So chapter 5 is exponential functions and logarithmic functions. You'll notice there's sort of like a progression through the course. So chapter 2, you kind of get introduced to functions and different transformations of functions, as well as other things. And then chapter 3, we move on to quadratic functions, well, really just quadratic equations and rational equations, so that in chapter 4, we can do polynomial functions and rational functions, and then inequalities. And now we're moving on to exponential functions and logarithmic functions. After this, we're going to do trigonometric functions. So there's these main headings of things that you are to take from this course. So the first thing we have to cover is, before we even get into actual exponential functions and logarithmic functions, you need to learn a new tool or kind of a transformation on a function. So we could have done this in chapter 1 really, but it's this idea of taking an inverse of a function. So the first thing we're going to look at is, what is an inverse? Well, taking an inverse from the standpoint of ordered pairs, or anything really, is interchanging the x and the y values of an ordered pair. So if you have a function or a relation h, which is 5, -8, -2, 4, 1, -7, and 6.2 and 3.8, the inverse of this function, which I shouldn't call functions at this point, we will dive into that later, but the inverse of this relation would be taking the x and y values and switching them. So the point 5, -8 becomes -8, 5. The point -2, 4 becomes a point 4, -2, and so on and so forth. So this transformation is taking your x and your y values and switching them. So if I gave you G, which is defined as the set of points 2, 4, -1, 3, and -2, 0, and I asked you to find the inverse of this relation, the inverse of G would be the set what? Right? What would I do to find the inverse? Pause the video and see if you can write out what the 3 new points would be. So the inverse of G, you would just take your points. Instead of 2, 4, it would be 4, 2. Instead of -1, 3, it would be 3, -1. Instead of -2, 0, it would be 0, -2. That is the inverse of those points, or that set of points. So now let's go beyond points, okay? So we just looked at this idea of inverse, just switching x and y's. Now what I want to do is explore equations and graphs. So an inverse relationship. So graphs of a relation and its inverse always do a specific thing, and I'm going to show you what happens. So if I asked you to graph the relation y equals x squared minus 5x, okay, I would plug in values of x and solve for y. I would use a table of values. So let's say I do that. For x is -1, I get a y value of 6, right? X is -1, I get a y value up here at 6, right? I plug in 0, I get a y value of 0. There we go. I plug in 2, I get a y value of -6, and I plug in 4, and I get a y value of -4. Now to graph the inverse, you literally just take those points and you switch them. So instead of -1, 6, I would have 6, -1. Instead of 0, 0, well, I still have 0, 0. This is what we call an invariant point. It's a point that doesn't change. And then our point 2, -6 would become -6, 2, right? There's our point there, -6, 2, somewhere in there, right? And then this point 4, -4 becomes -4, 4, -4, 4. And so you get this inverse graph. Now, if you've done it correctly, what I want you to notice is that the graphs of a relation and its inverse are always reflections of each other over the line y equals x. So I've drawn this dotted line here, which is the line y equals x. And you can see that the graphs are reflections of each other across this line, and that they cross the line at any invariant point. So like here I have a point 0, 0, and here I actually have a point 6, 6. So that's a point where you switch the x and the y values and they stay the same. The other part of this is, to graph the inverse, I just looked at the table of values for my original relation and I switched the x and the y values. Well, I can also find the equation of an inverse relation by switching the x and the y values. So if I was to put in for y, x, and to put in for x, y, I end up with x equals y squared minus 5y. This is the equation of the inverse, and I could check some points. You know, if I plugged in x is 6, and I plugged in y is -1, it would make the equation true. Now, if I was actually trying to plot using this equation, I would not plug in values of x and solve for y. I would plug in values of y and solve for x. Okay? The last thing I want to talk about in this section is domain and range. So I want to look at the domain and the range of the relation and the inverse relation, and I want to see what happens. So if I asked you to find the domain of your blue graph, your original relation, well, it's y equals x squared minus 5x. There's nothing I can't put in for x and square. There's nothing I can't do minus 5 times. So in other words, I know just from my equation that my domain is going to be negative infinity to infinity. The only things that restrict a domain are x's in a denominator and x's under a radical sign that has an odd root, sorry, an even root. Okay, this one doesn't. I could also look at the graph and see that my arrows point endlessly to the left and endlessly to the right, so I know my domain is negative infinity to infinity. Then if I was trying to find the range, I'm looking for my possible y values. Now my graph starts down here at -6. So I would say that it's -6 with a closed bracket or a square bracket all the way up to infinity. Now what happens when we find the range of our inverse graph? Well, if we look at the graph, we can now see that the domain starts here at -6 and goes all the way to right. So I would say the domain is -6 to infinity. And then round bracket. And then my range, if I look at it, these arrows keep pointing up, they keep pointing down, and my range is negative infinity to infinity. What do you notice happened? Hopefully you notice that the domain switched to the range and the range switched to the domain because the x and the y values switched. So the domain and the range switched. So as soon as you know your domain and your range of your original relation, you can find the domain and the range of your inverse relation as well. It's a good way to check if you've graphed correctly. So now I want to do just that. So here's a graph. This is your relation, and I want you to graph the inverse relation, and then I want you to state the domain and the range of the relation and the inverse relation. So what we just did on the example before, except it was done for you, I want you to do here. Now, if you're questioning how to start, think about chapter 1. When you did transformations, you needed to find key points. So let's look to see what the key points for this graph would be. I'm going to put these in blue. So the key points of my original relation is there's a key point here at -7, 3. I have a key point at the top of this, like a relative min, which would be here at -4, 6. I have another key point here at -1, 3. I would go all the way to the end of this line to here, to this point 3, -1. Then I would put one in the halfway up just so I know where to make that curve to be specific. So there's a point here at 4, 3. And lastly, the end of the curve up here at 6, 6. So now what I want you to do is graph the inverse relation, and then I want you to state the domain and the range of each. So pause the video. All right, so for me, I'm going to look at this and I'm going to say this point becomes 3, -7. I'm going to graph it 3, -7. And then this point becomes 6, -4. 6, -4, and then this point here becomes 3, -1. 3, -1, so it shares that guy. So then I'm going to sketch this. Sorry, I'm looking at the symmetry here. 1, 2, 3, 1, 2. Oh, it is. It seems off to me. Okay, I'm going to sketch that, and then I'm going to move on to the next set of points. So this one's going to become -1, 3, -1, 3, shares this whole line. And then 4, 3 becomes 3, 4, 3, 4, and 6, 6 stays 6, 6. There we go. Okay, so that is the graph of the inverse. Now the next thing I want to do is look at domain and range. So the domain and range of my original relation, so the domain of the original relation, it starts here at -7 and it ends here at 6. So it's going to be -7 to 6. The range is starting down here at -1 and ending up here at 6. So it'll be -1 to 6. So now, if I wanted to find the domain and the range of the inverse, I can just look here and say, okay, Well, if my range was -1 to 6, now my domain is -1 to 6. And if my if my domain was -7 to 6, now that's my range. And then I could check my graph to make sure that worked. So my domain would go -1 to 6, that works out. And my range starts down here at -7 and ends up here at 6, and that works out. Great work. Okay, so the last thing before we take a break is we want to start using the word function, okay? And it's kind of been spattered throughout because it's hard not to start talking about functions. But the idea is that up until now, we've just looked at this idea of an inverse. It didn't matter whether it was an inverse of a function or whether the inverse was a function, but now it's going to start mattering. So we are going to be looking to see if these are called one-to-one functions. A one-to-one function is specific in that the original relation is a function and the inverse is a function. So if you look at these guys, right? So if I just looked back to like even just this one, yeah, my original graph was a function, right? Y equals f of x. The black graph is a function. But as soon as I reflected it over the line y equals x, this pink graph, it no longer passes the vertical line test. It's not a function. So this is not a one-to-one function. So we can't use what's from this point of the note forward for a graph like this one. Okay? Instead, we would just call them relations. But what we want to focus on is graphs where the original graph is a function and where the inverse is a function as well. If your inverse is a function, well, if your original graph is a function, you can use f of x. And if your inverse is also a function, now we get to use this new notation, which is f to the -1 of x, and it is not to the -1. That's just how we write it. This is not read f to the -1 of x. This is read f inverse of x. The -1 is not an exponent, because if it was, then f to the -1 of x would be equivalent to 1 over f of x, and it is not. This is actually its own thing. This is called a reciprocal transformation, which I really wish we did, but we didn't. Okay, but this is a reciprocal transformation, and that's the notation that you show to say, hey, I want you to graph the reciprocal. This is the notation we use if we want to say, hey, I want to graph the inverse. So what are some properties of one-to-one functions? Well, if a function is one-to-one, then its inverse is a function and the original equation, right? So the original graph is a function and the inverse is a function. Now here's something specific, is that you can tell if a graph is going to be one-to-one if the original function increases or decreases. It can't do both. In other words, if I go up here and I look at my quadratic, my blue graph is a function. It's a quadratic, right? It's a quadratic function. But this graph increased and decreased. Meaning, if you came in it from the left, you can see that it's decreasing in y values over x, and then it increases. And because it made that change, we know it's not going to be one-to-one, right? Its inverse is not a function, because when we switch the x and y values, those increasing and decreasing functions, or increasing and decreasing parts, overlap each other, right? So that's just a rule. So no quadratic is ever going to be one-to-one. But a linear graph is, right? Linear graphs either increase or decrease, and so they are one-to-one as long as they're not horizontal or vertical lines. The quickest way to tell if something is one-to-one is you make it pass what we call the vertical and the horizontal line tests. So the vertical line test we know, right? I chose 4 functions down here, right? These are all functions. They pass the vertical line test. What we want to check is, do they also pass the horizontal line test? So that when we switch the x and the y values, your vertical line, would be a horizontal line in the original function, which would be the vertical line of your inverse. That sounded so horrible, I apologize. But what it is that if I draw a vertical line, right, your original graph is a function. All good. If I draw a horizontal line, right, then I'm checking if the inverse is a function. Because if I switch the x and the y values, this horizontal line is the vertical line of the inverse. That came out better, okay? But it failed. So this graph is not one-to-one. Okay, what about this one? If I draw a vertical line anywhere, it passes. So its original function is a function. But if I draw a horizontal line, does it pass? Do I pass through more than one point? Nope. So this one is one-to-one. Okay, so pause the video, try these last two. Okay, hopefully you pause. So they both pass vertical line test. So let's try the horizontal. Horizontal, fail, not 1-to-1. This one passes vertical, horizontal right here, fail 3 times, not 1-to-1. Okay, so you are now going to go and practice part 1. You'll notice I tried really hard not to ask questions where you had to graph the original function from an equation, just because really what we want to get here is this property of inverse, and so it's easier to see when something's already graphed for you. So I tried to make it specifically that you only are expected to know how to graph maybe lines, or I asked, section B only or something like that. But yeah, give these ones a go, and then we'll do video 2.